Okay, in this video we're learning about the index laws. Now there's a whole bunch of index laws here, and some of them may look familiar, some of them may not. I know that occasionally this is covered in the Year 9 curriculum, although I'm sure it wasn't our favourite topic back then. So we're going to review these right from the start, and hopefully they'll make a lot of sense this time around. So we've got the first index law, which is basically saying that if you're timesing two powers, you add the powers. So this could be something, for example, like if you're doing 2 squared times 2 cubed, that is the same as doing 2 to the 5. Now let's actually check that this is correct, because 2 to the power of 5 is just 2 times 2 times 2 times 2 times 2, which is 32. Whereas 2 squared is going to give us like 4 times and 2 cubed is 8, which is also 32. So this stuff all works out. You could have something like a to the 72 times a to the 8, and you would get a to the power of 80, because you would add those powers together. Okay, so that's the first to the next law, and if you want proof, it's actually not too bad. A to the m times a to the m is going to be a times a times a, and that is m times by a times a times a times a, and that thing there happens n times, which is equal to a times a all the way through. Well, if you have m times and then n times, you've got m plus n times. So that's sort of how you go about proving these index laws. And you could try and prove the others as an exercise. It's pretty similar. But let's do examples of all the other index laws here. So we might have a situation like 3 to the power of 5 over 3 squared. Well, you take the powers, so you're going to get 3 to the 5 take 2, which is 3 cubed. If you want to know what number that is, it's 27. You could also have something like a to the power of 7 over a to the power of 2, gives you a to the power of 5. Next index law we have, we'll do an example of this. So we could have something like 2 to the power of 3 to the power of 4 gives you the same as 2 to the power of 12, because you do 3 times 4. If you want to check this, you could do 2 cubed to the 4. If you think about what that really means, it's 2 cubed is 8 to the 4. And if we look up 8 to the power of 4, well, that's 4096. And if you look at 2 to the 12 on your calculator, that is also 4096. You could have a situation like this where you've got x to the power of 2 cubed. That would be the same as x to the power of 6. Alright, so that's index law number 3 in action, and then index law number 4 we'll have a look at. So number 4 tells you this, a times b to the n. So you could have something like 2 times 3 to the power of 5 would be the same thing as 2 to the 5 times 3 to the 5. Now if you want to step out what that actually is, so you'd have like 2 to the 5 times 3 to the 5 gives you this big number. Or you could have 2 times 3, which is 5 to the 5. And we could check what that is. There we go, which is actually different. Because 2 times 3 is 6, not 5. That's my bad. Okay, so let's try 6 to the 5, and hopefully it will be the same. There we go, 7776. Great. Now you're actually doing this already, because when we did something like binomial expansions, if we had 2x plus 3 and we squared it, we'd have 2x squared plus 2 lots of 2x times 3 plus 3 squared. And when you did this step, I always told you have to square the 2 and you have to square the x. So this actually becomes 4x squared. The reason that's true is because of this index law. Okay, next index law we have is basically the same one, but with divide. So you could have something like 6 over 2 to the power of 7. Well, that would be the same thing as doing 6 to the 7 over 2 to the 7, whatever that ends up being. Or if you want to do it the other way, it's the same as 3 to the 7. So those two things should match. Okay, the next index law we're going to have here is a bit of a weird one. It's that anything to the power of 0 equals 1. So let's check it out. 2 to the 0 equals 1. 3 to the 0 equals 1. 123 to the power of 0 equals 1. Pi to the 0 equals 1. Anything to the 0 equals 1. Except for 0 to the 0, that is undefined. It's a bit weird, that one. So if you have x to the 0 in an equation, you always just replace it with 1, and you're sort of assuming there that x is not 0. Bit of a strange one. If you want to try and prove this is true, so a to the 0 equals 1, is that true? Maybe what you could do is you could think about a cubed over a cubed and use index law number 2, and then the proof should fall straight out. Okay, next index laws. we've got this one about negative powers. Now, a negative power basically means a fraction. So 3 to the minus 1 is a third. 7 to the minus 1 is a seventh. X to the minus 1 is 1 over x. And if you want to start doing fancy stuff like 2 to the minus 5, that is 1 over 2 to the fifth, which is 1 over 32. Or if you want to be real fancy, like 7/8 to the power of minus 1, you just flip it. So what you're going to get is 8 over 7. Or if you want to do 7/8 to the power of minus 2, you would get 8 squared over 7 squared, which is 64 over 49, something like that. All right, last index law we have is about fractional powers. So we could have 2 to the power of a half. That's the same as doing root 2. So you can actually think about this by using the index law where we thought about like a to the m to the n is a to the m times n. So in theory, if you do root 2 and you square it, you should get back to 2. That's like the definition. And this thing here is 2 to the half. And then if I square it and use the other index law, I'm going to get 2 to the half times 2, which is actually 2 to the 1. So all these index laws are consistent with each other. So if you wanted 9 to the power of a half, that's going to be square root of 9, which is 3. And we can actually see that if I do on my calculator 9 to the power of a half, you're going to get 3. Or if you do 9 to the power of negative a half, well, the negative is going to put it under a fraction. And then you're going to get 1 over root 9. So that becomes 1 over 3. And you can always check these on the calculator. 9 to the power of negative a half does indeed give you a third. Okay, and if you want to convert that to a fraction, there we go. Okay, just a little bit strange. If we have something like 2 to the power of a third, this is going to be the cube root of 2. And what that means is this is the number that when you cube it, you get 2. So if I do 2 to the power of a third, whatever that ends up being, that number, and I do 1.25992,105, and I cube that, I should get back to 2 pretty much. If you want to do something really fancy, like 2 to the power of 5 over 6, that's going to be the 6th root of 2 to the power of 5. Or if you want to write it as the 6th root of 2 all to the power of 5, both these are correct. So fractions work a little bit weirdly with square roots. You can do cube roots pretty straightforward. If you do like 27 to the power of a third, that actually ends up being 3. Because if we look at 3 cubed, that gives me 27. And if I want to do 27 to the power of 2/3, that's going to be, well, the cube root of 27, and then we're going to square that, which we know the cube root of 27 is 3, so that is 9. So if we look at 27 to the power of 2/3, that's 9. Or if I want to look at 27 to the power of minus 2/3, that's going to be 1 over 9, something like that. Okay, last one I want to do is just simplify this absolutely horrendous thing. But if we just use our index laws, it should be fine. So we have this horrible equation. Let's simplify the inside first. So we'll do our numbers. 6 over 3 gives us 2. We got a squared over a, so that's just going to leave us with 2 minus 1. So that's 1 as the power. Now we got b to the 3, take away minus 2. So that's b to the 5. And we've also got c to the 6 on the bottom. I just might write that as c to the minus 6. And then all this is going to be to the power of 4. So that's going to be 2 to the 4 is 16. A to the 4 is a to the 4. B to the 5 times 4, so that's b to the 20. And then c to the minus 24, because we got minus 6 times 4. And if you want to get extra fancy there, that's 16a4 b20 over c to the 24 if you don't like that negative power there. So that's sort of how you'd simplify something horrible like that.